Okay, this lecture we're going to talk on black hole evaporation, sort of a mixture between black holes and quantum mechanics. That is a lot of conjecture, but it's a lot of fun conjecture, and people have done a lot of thinking about this. So I will tell you now, this is Physics X, though. This is Extraordinary Concepts in Physics, a class being taught at Michigan Tech, and there's lots of nearly 15-minute segments that are going up on the web, and this is one of them. So I'm trying to be light on math and heavy on concepts. If you're locking onto this, good for you. Have a look through the different lectures, find one you like. You can find them here, you can find them on iTunes, and if you can't read this, then you can go to Starship Asterisk, search for that on Google or something, and then after that search for Physics X, and you'll find a long list of lectures, hopefully. So we'll first start off with a question, which I sometimes want to do. Black holes and entropy. This is something I've wondered about. So you drop a hot ball into a black hole. You have that power. And then you drop a cold ball into an identical black hole. The balls were otherwise identical. Are the black holes still identical? Yes, black holes can carry only mass, charge, and spin would be the first answer. No, now they're different. Hey, you said you were only borrowing those balls. I want you to go back and get them. So unsatisfactorily, we're going to have to wait for the end of this little segment to get to that, but I will say that it's questions like that and noticing that the surface area of black holes is very similar to entropy in the sense where if you drop stuff into black holes, the surface area of the black hole will increase. And if you have a system, the entropy of systems only increase, closed systems. So thinking like that got entropy involved in black holes, and then Bekenstein was pretty good with that, and then Hawking came around and said, okay, here's another step. Why can't black holes emit radiation like thermal radiation as if they have a temperature? So this theory is still somewhat controversial. Some people say some of the, well, however, it now might be even more controversial to assume that they're extremely black and they don't emit anything. Exactly how this happens, again, is not completely well known. We know that virtual particles exist everywhere in the universe. Now, black hole evaporation is an attempt to include quantum mechanical aspects in gravity. In gravity, the best theory of gravity we have is general relativity, which is not a quantum theory. It doesn't have virtual particles. So this is a little bit like stapling on two things and seeing if you can get it to match up as best you can. It's not a complete theory. However, if there were virtual particles around black hole event horizons, particularly virtual gravitons or something else, you might get sometimes pairs of virtual particles. One of the virtual particles could fall in and the other could go to infinity. So the one that falls in might be considered to have some kind of dark energy, a repulsive gravity type force, and the one that comes out would be normal energy. So you had a virtual pair, and we'll get to something called Unruh radiation in the future, whereas if you have an accelerating field of virtual particles, you're going to shake some into the real domain. So it could be that the gravity of a black hole is a little bit like that, and some of the virtual particles are shaken into the real domain and become the evaporating radiation, and others have essentially negative mass. Well, I don't like to use negative mass so much. They have dark energy, which would then have a repulsive force and cancel out part of the gravity, attractive gravity of the black hole. So it's pretty cool, though, to think about some of these things. We can go to some of the attributes. First of all, we need to back off. There will be other lectures on black holes. They might not be up now, but if you're seeing this in the future of October 2010, you can look for the black hole lectures or read stuff on Wikipedia about black holes. There's lots out there. So a black hole has what's called an event horizon, a source field radius around it, typically. And so many times black holes are thought of as just being a point mass in the center, surrounded by an event horizon. I don't always like that picture because anything is the point, as we know, as I've said in other lectures, means that its radius is essentially too small to measure and means we don't know the radius and we get into regimes where we can't really go. We do know that if you were to emit light inside an object that has a compressed one solar mass, then that light would not be able to get out, and you would have a region of darkness where light can't get out. So for the sun, this would be 3 solar masses times 1 mass sun is equal to, well, it goes like mass. So for the sun, it would be 3 kilometers. So if we wanted to make our sun into a black hole, which could be a school project, it could be something you'd want to do for the science fair, you would have to then compress the sun into 3 kilometers. Sun's about 700,000 kilometers. So you might need a budget and some spaceships. You might need some volunteers. It might be easier to take the Earth and compress the Earth. Every object has a black hole radius, if you consider it's whatever mass it is. So you yourself have a black hole radius. So does the Earth. So the Earth, if you wanted to compress the Earth into a black hole, again, difficult, not for children. You would probably get something around 1 centimeter or so, maybe this big, depending on how big your screen is. However, the radius of the black hole would depend on its mass, and it's linearly dependent on the mass. The greater the mass, the larger the radius. The volume of a black hole inside that goes as the mass cubed, 4/3 pi r cubed kind of thing. All right. So now that we know what the mass is, and now that we know what the volume is, you can compute the average density. So you divide one by the other from the previous screen, and you find out the average density of a black hole drops as the mass squared. So for that science project where the sun was compressed into a black hole, a 1 solar mass black hole would have an average density of nuclear matter. Now, it could be that all the matter is very near the center in very near a point-like object. But if you were to average it out all inside, it would have an average density of about nuclear matter. Now, we know stellar objects like white dwarfs and neutron stars that have approximately constant density. And so if you were to turn up the average density there, you could actually get a black hole solution from the outside. So it might not be so absurd to have something that's constant density inside. Let's say you were to make a much larger black hole. Would the density go up or down? Intuition might say, well, if you have a supermassive black hole, you should have super high average density. But actually, since m is in the denominator here, density, as we said, drops off as mass squared. So the average density of a 10 to the 7 solar mass black hole, which might be found in the center of a galaxy, would be the average, about the density of water on the average. Here's something that's really spooky. If you were to take our entire visible universe, what we can see, where the photons come to us from, and you were to smear that out, and you were to consider what that mass is, and then you can say, okay, let's now consider it a black hole. What would be the average density of that black hole? You would find a coincidence that the average density of our universe as we know it is about the average density of a black hole if it would have the radius of our universe. So given that, looking at it from the inside, so far as we can tell, we might be living in a black hole. Average density goes way down. Okay, black holes evaporate, according to a theory elucidated by Stephen Hawking. And so you can work through the power, and you can get the power goes as 1 over the mass squared, again, in terms of watts. So if you had an asteroid, if you were to compress an asteroid into a black hole, even easier than the Earth. So we're getting into easy stuff to compress now, so I don't want any complaining. 10 to the 15 times the mass of the sun, it would glow, it would actually glow with about the brightness of a 100-watt light bulb. So asteroid would glow like 100 watts. So the power, well, okay, so at some point, though, we know there's an accretion power. The microwave background, which we'll talk about in other lectures, comes from every direction. It's all this energy coming from all this direction, from everywhere from the Big Bang. That's going to create a photon field that's everywhere, and it's going to be absorbed by a black hole. So the turnaround point is at about actually 10 to the minus 8th solar masses when the microwave background radiation exceeds the evaporating power of a black hole. So you're getting more energy in than coming out at that point. Black holes in vacuum, though, would evaporate, totally evaporate after some time. So all the black holes we know, all we have to do is wait them out. Unfortunately, for things like the sun, you'd have to wait more than the age of the universe. So I don't know if you're prepared to do that, but you need some rations. However, when things get lower down, it would take, let's say, a bus-sized black hole about 1 second to evaporate, and it would be emitting an average of about 10 to the 22 watts. So that's really bright. So that's why we say now that if this Hawking radiation is correct, that black holes at the end of their lives, they don't go quietly into the good night, they explode. So these things that we thought were black, now the common wisdom is that when they come to the end of their lifetime, they just essentially explode. However, some people, there are things, many of the photons that would come out would be gamma rays. So people say, well, we know there are explosions of gamma rays, and they're called gamma ray bursts, and we will get to that too in other lectures. So in these gamma ray bursts, are these exploding black holes? Well, it's pretty clear exactly how bright this is, 10 to the 22 watts, there's so many. So we know the distances to gamma ray bursts, and the gamma ray bursts we know the distances to they're too far away to see these explosions. We would only be able to see black hole explosions much closer by. So we don't think that the explosions we see as gamma ray bursts are black holes that are evaporating quickly at the end of their lives. So here we come to another aspect of this, information paradox, going back to the beginning. Does the radiation that comes out of a black hole carry the information of the matter that fell in? Similar to the problem at the very beginning. If you drop in a hot ball and a cold ball, maybe the cold ball in some way has some coded information in it or it has different entropy, what happens? Is the information conserved? Do black holes, as I said before, carry only mass, charge, and spin, which is called the no-hair theorem? Or you woke me up to ask me, what? Drum roll, please. It's controversial, as I've indicated. Obviously, we don't have a black hole here to experiment with. There's some interesting books about what would happen if there were a black hole on the Earth. If someone was to create one. The Krohn experiment is one. But we don't have one. We can see things that we would guess would be black holes far away, but we don't have the ability to control any of the experiments and find out firsthand what's going on. So the information that's dropped into a black hole, we're not sure what happens. It might be lost. So all of this evaporation stuff might be wrong, though no-hair theorem might be completely right in the sense that black holes only have charge, mass, and spin and never anything else. It might be, and people analyze these, the information is radiated gradually away during the evaporation process. It might be that only at the very end, when it gets right near what would have been a singularity, would the information finally come out. It could be that when a black hole evaporates, there is a nugget left over, a Planck mass nugget, and we've gone over Planck mass in a previous lecture. It's small, but it could be there, and somehow that might inside of it encode the information that went in, including the entropy. Maybe there's a massive remnant that comes out. It's something like a neutron star, maybe a little bit smaller than a neutron star. Although if you get too much smaller than a neutron star, it again looks like a black hole. Here's one I haven't analyzed much, but I've read about a little bit, Trapped in a New Baby Universe. Well, you can look that up under information paradox and see what's being talked about there. Quite possibly, we don't really know. There is no quantum theory of gravity, and so the answer might come out only when the complete quantum theory of gravity is known. And even then, we might only know some basic equations that might take quite a while to figure out what happens. Although people will be looking for that, because this gets to the heart of information and entropy and the battle between gravity and entropy, and some of the concepts at the core of physics have a tendency to fight here. And that's one of the reasons why this is so interesting. So we have guesses as to what the answer is, but we don't really know what happens to information that's dropped into a black hole. And with that, I'll leave you till next time, and see you then. Bye.